My name is Fangjin. I'm a software engineer at Metamarkets. And Metamarkets is a real-time data analytics startup, and we're located in San Francisco. I actually think this is the second time that we visited the AMPLab. I think we did a talk here around 2 years ago-ish. So a few weeks ago, HY, Matei, and TD actually visited the Metamarkets office, and they taught us a whole bunch about Spark Streaming. Since then, we've actually been trying to get Spark Streaming integrated and working with our own internal data store, which is called Druid. As of a few months ago, we actually open sourced Druid, and the purpose of this talk will be around sort of what Druid is, why we decided to build it, and some of the architecture behind it. Right, so a brief overview of what I'm going to talk about today, sort of the motivations of why we decided to build Druid in the early days of Metamarkets, how it works, and sort of its real-time capabilities. Real-time is this term that the industry has kind of overused, and it really has like no meaning anymore. I've actually heard of SAP's HANA as being referred to as a real-time database, which I thought was kind of funny and kind of ridiculous as well. But to make it more ridiculous, I've been calling Druid a real-time database for real. Okay, so some of the motivation behind why we decided to build this thing called Druid. In the early days of Metamarkets, we wanted to visualize large quantities of data. And Metamarkets was founded about 3 years ago. And around that time, we were only a handful of developers. And we wanted to find like a backend system that could power a front-end dashboard to visualize data. So at that time, we tried a couple of different options. One of the first things we tried was your typical relational database management system. Actually, at that time, the solution that we went with was EMC's Greenplum. The setup that we had was we had a star schema, we did some pre-computation and pre-aggregation, and we had some level of caching as well. And what we found was queries that were sent against cache data or against like the pre-aggregate tables generally performed pretty well. Anytime we had to do sort of a full table scan, things were not as good. And it turned out that we had to do these scans like fairly often. Another thing about the solution that we're trying, which was Greenplum, was they had this like single node community edition, which was free, and they charged a lot more money for a distributed solution. The problem was we were a very small startup, we didn't have a ton of money, and we didn't want to give it to somebody else. So the next thing we tried was Nosql, and this was about 3 years ago, and the Nosql solution we tried was HBase. So the setup was we would pre-compute like different permutations of dimensions. We would store those values in HBase, and query speeds were generally pretty fast because all you were doing was like effectively a key value lookup. Some of the problems that we found with pre-computation is as data volumes grew and as your data set introduced more and more dimensions, the pre-computation time became exponentially more expensive. And it was to a point where like it was becoming prohibitive to scale with the data, with the increased data volumes that we were getting. So sort of those are just some numbers of what we saw when we were experimenting with HBase and pre-computation. So it was at this point that we kind of stepped back and looked at the problem again, and we kind of decided that maybe we should try and build our own thing, which we call Druid. And the purpose of Druid was to solve what we thought was the easiest of the two problems that we faced, which was scan times were pretty slow in relational database systems. So Druid is named Druid because the lead architect of Druid played a lot of World of Warcraft. And there's really no clever like acronym behind the name. So what Druid is distributed, it's column-oriented, and you're probably thinking, okay, I've heard this before, but why did you guys build another one of these? I'm going to try and convince you that Druid does do a few things pretty well. By the way, that stick figure dude is our logo, and our logo is a work in progress right now. So some of the key features of Druid. Druid does low latency data ingestion. I think it can be somewhat classified as a streaming database. You can query data as soon as it is ingested. Druid was designed from the ground up for sort of like the OLAP style workflow. It does multi-dimensional data exploration, and it does like aggregation sort of natively built in. Druid is also designed to be a highly available system, so you can push like software updates without any downtime, without any loss of data, and like the system will recover from various sorts of failures. Okay, so a brief overview of the architecture of Druid. Druid has a shared nothing architecture. The nodes are independent and self-sufficient. We have several different classes of nodes, and these nodes really serve like different types of functions. For example, we have coordination nodes, which are responsible for load balancing, for replication, etc. We have historical compute nodes, and what historical compute nodes do is they load data that's not considered recent, and this data might be like anything that's older than 1 hour to some point in the past. For very like recent data, we have a different type of node called real-time nodes. All data within Druid must have some notion of time, so we require that all our events have a timestamp. And the way we shard our data, the way we chunk up our data is into these blocks known as segments. Segments always represent some interval of time, so you can have a segment for yesterday, you can have a segment for some previous hour. Most of the segments that we build are immutable. For any like historical, not recent data, we can build immutable representations of that data, and it gets us away from problems like having to deal with reconsistency. The sort of downside of having immutable data is if you require some update for some event that occurred in the past, then your only option is basically to rebuild the segment. Some segments are mutable, but those segments tend to cover data that's extremely recent. And when I say like extremely recent, I'm talking like the most recent 10 minutes or so. So because we have this general notion of like immutable segments within a cluster, we use multi-version concurrency control as our swapping protocol. Some other things that we do, we have intelligent load balancing and replication. What I mean by intelligent load balancing and replication is we looked at how our customers use the system and sort of the query patterns that resulted from that. We noticed that almost every customer tends to care about recent data a lot more than historical data. And because segments are broken up basically on an interval basis, we can replicate and load balance based on how recent the segment is. Druid also has a plugin architecture where you can plug in different algorithms and different query types. For example, we've built some approximate algorithms for cardinality estimation, for top K, and so forth. Okay, so in the most basic Druid cluster, you have a set of historical compute nodes. And what historical compute nodes do is they load and serve historical data. And historical data is, as I mentioned, really data that's older than an hour, and this data is represented in some immutable form. On top of the historical nodes, we have a layer of broker nodes. The broker nodes do like basic scatter gather. The architectural pattern is fairly common. Broker nodes have an idea of what data lives on which nodes. So when a query comes in, it can appropriately forward that query into the nodes which actually serve the data. Sort of another class of nodes that we have are these real-time nodes. And real-time nodes are a little bit different in the sense that they do ingestion of data, as well as making that data available for querying. The data that real-time nodes deal with are a much smaller subset of like a larger data source. So real-time nodes collect data, and then periodically they build immutable representations of that data, and then hand it off to the rest of the historical cluster. When you issue a query from now into some point in the past, that query will likely hit a subset of real-time nodes and a subset of historical nodes. I think one of the other things that we do that's pretty cool in my mind in Druid is how we do filters. And if you think about like a where clause in SQL, right? All it really is some Boolean expression of terms where each term is like this column value. This column is equal to like this column value. So what we've done is for all the column values, we actually build a bitmap index, and this bitmap index like indicates in which rows a column value is seen. So when a filter comes in and we take these bitmap indexes and we do Boolean operations on top of them, that the resulting output is a smaller subset of rows that we actually care about and have to scan. These bitmap indexes, we compress them using an algorithm called concise. And concise is an extension of word-aligned hybrid, which is really just a variation of run length encoding. We always do operations over these bitmap indices in their compressed form. It tends to be much faster to do these operations this way, and we don't have to suffer from the problems of, or the costs of doing decompression. Cool. A little bit about availability. Druid is fairly configurable. You can increase and decrease your level of replication. You can adjust your levels of performance based on the underlying hardware. Similar to like other data stores such as Dynamo, you can have different storage adapters to represent your data. For example, you can have an all-in-memory storage for your data, or you can have like a memory map representation of your data. Druid is able to support like multiple software versions within the same cluster. It's one of the ways that we do rolling restarts, so not everything has to be on the same version. And then it's built to run on commodity hardware, so the process of growing or shrinking a cluster is just starting and stopping some processes. Okay, so sort of the next section here is just talking about Druid's real-time capabilities. Real-time, I think, is a word very much like cloud or big data. It has like no concrete definition. Everybody like wants it, but nobody really knows what it is that they want. For us, we kind of define a real-time system as having two attributes. One, what we've noticed with our customers is if they are able to issue a query and if they can get some response to that query in about 0 to 5 seconds, they're pretty happy. Two, if an event occurs, and if the system is able to ingest that event and make it available for querying somewhere between like 0 and 15 seconds, we find customers are pretty happy. So how Druid does real-time is there's a separation of concerns. We have a class of historical compute nodes which deal with immutable data, and we have this class of real-time nodes which is like streaming in data and building immutable representations of that data and handing it off to the historical nodes. The setup that we have in place is, it doesn't show up very well, I think, on the slides. But we have some producer of data, and they feed a data stream to some intermediary like message bus. I actually think I read this from one of the AMPLab papers that you guys refer to this as like upstream backup, which I think is a fairly common practice in the industry. There are some issues with upstream backup that was discussed. For example, it's really what happens when a node fails and has to reread data from the message bus. So we've actually engineered some solutions on our side to kind of address this problem. But the basic setup is data stream goes to some message bus, and then you have the real-time nodes which read from that message bus. So, so how our real-time nodes work is they read in a data stream, and periodically what they do is they persist the data they've collected onto disk. So the idea would be a real-time node is collecting data for the current hour. And then every 10 minutes or so, it builds a mutable representation of the data it has collected, and then persists that chunk to disk. The idea there of periodically persisting to disk is if a node fails and it recovers, then we're minimizing the amount of data that needs to be reread from the message bus. There's a separate background process that runs less periodically, and it collects these immutable chunks that were built during the current hour, and then uploads them to some like permanent storage, which we call deep storage. So permanent storage could be anything from like S3 to HDFS. Somebody in Europe actually got this working with RIXCS, which was pretty cool. Sorry, excuse me. So going back to that example, if we're collecting data for the current hour, we persist these immutable chunks every 10 minutes, and then at the end of the hour, we build a immutable segment which represents all the data we've collected over the hour, and then we hand that off. And as like this entire process is occurring, all this data is still available, and it's available for querying. The largest real-time cluster actually that we know of with this setup is at Netflix, and I think they are doing 2 terabytes of raw events per hour. So in terms of high availability, some of the things that we do is replication of real-time data, and that's a pretty simple concept. You just have multiple nodes that read from the same message bus, and they collect the same sort of events. Some of the problems there is, of course, if all nodes reading from the same message bus goes down, then you lose your data. One of the other things that we're trying to minimize is the amount of data that's being read should a node fail and then recover. Because we periodically build like immutable chunks, if a node fails and recovers, it can load up those chunks right away and then do a read from the message bus for a much smaller subset of data that was lost. Sort of the final point here is in our own production systems, we always have this accompanying batch process. And the batch process may run once a day or once or twice a day. And the idea behind it is just to do any cleanups and fix any problems that may have occurred because of real-time ingestion.
What kind of problems are
like for example, like you can get duplicates of data. The message bus that we run with in production is Kafka. And we've seen instances where we just have duplicates, and it's very hard to dedupe on the fly. So as I mentioned, Druid is an open source project. There are some links up there that you probably can't see very well. But if you're interested, you can read up on Druid. We have a paper out as well. There's a meetup that's occurring, I think, tomorrow, where I'm actually going to talk a little bit more about how Druid does like real-time stuff. And that's it. Thank you.
Any questions?
Yes. Hi.
I have some questions about filters.
Yeah.
I think it's a general question, but I'd like to know how you guys handle it.
Okay.
So you have, you say you have a bitmap on each column, right?
Yeah. We have a bitmap for like every value in every column.
Okay.
Yeah.
So given a filter, you can determine which subset of rows you want to repeat.
Right.
And then if these subset of rows is everywhere, across different partitions, how do you efficiently get them?
So,
So per partition level bitmap.
yeah. So yes, like so the bitmaps are always built based on like a segment basis, and like sort of the fundamental storage unit in Druid is the segment. So what they indicate, so a query may hit one or multiple segments, and each segment maintains its own bitmap index of column values and like which rows of the segment that you actually have to scan. So when you send a query to hit like multiple segments,
So you basically figure out segments. As,
yeah, we filter out rows that we have to scan within a segment. Then we scan those results. Does that make sense? Am I losing you?
So you figure out the segments. And for the segment that involve the subset of rows, you have to scan the whole segment, right?
You don't have to scan the whole segment. So let's start at a higher level. You issue a query for like 1 week's worth of data, right? And that 1 week's worth of data might translate to like 7 segments if each of those segments is representing 1 day. Sort of the same filter set applies to all 7 segments, but all 7 segments may have like different bitmap indices of which rows actually correspond to that filter set.
Yeah.
So when you scan those 7 segments, then what you're doing is for each segment, you're scanning a subset of the rows of that segment which pertain to the filter set.
Yeah, how do you scan the subsets, the rows in that segment without scanning the whole segment?
Oh,
You have an index or something? Are you?
yeah, so the entire bitmap is an index of like which rows you have to scan, of like which locations in memory you have to scan effectively. Does that sort of
Yeah.
make sense?
Good question.
Yeah.
So do you assume fixed length data? And the other one is, because otherwise it makes it harder to maintain the index, right?
So yeah, so like every segment, like we have a row count of how many rows in total are in the segment. And then the indexes are built on top of like that row count.
No, but for each record,
Oh.
you have variable length data.
So we do like dictionary encoding of the dimension values. So in that sense, yes, our data is like fixed length.
So you're assuming basically everything has some lower cardinality that's not going to blow up your...
Yeah, so we shard segments based on dimension cardinality as well. So if the cardinality dimension exceeds like a certain threshold, then we will like break it up.
But what about like scalar values, like the timestamp itself?
So you can't really like filter on the timestamp itself. So we actually don't build any unique indexes. Like you can query for a certain interval of time, but it's not like I want. We don't really support queries where it's like I want this timestamp value or this timestamp value and like this timestamp value. If that makes sense. So the bitmap indexes are usually built for like what we label as like dimensions, and we have this notion of like a timestamp, a dimension, and a metric. Dimensions, for the most part, they're just strings.
Wait, but let's say let's say I'm running a query that's filtering by revenue, right? And for each point of sales, I want to check how many sales have greater than maybe $100,000.
Okay,
right?
so yeah, so that is a sort of a different problem than the filter set I was describing. So the filter sets that we built are more for the sense that I want to filter on publisher equals like Google.com or like advertiser equals like Facebook, like along those lines.
This is pre-aggregation filters.
So we store like rolled up data. There is some level of roll up that occurs before like data aggregation.
do it pre-aggregate.
Right, but like so there is like some summarization that occurs before entering Druid, if I understood your question correctly.
So is your segment mainly memory resident or?
It's memory mapped. It can be purely in memory, but we just found it was too expensive to scale all data in memory.
Yeah, so if you did it, still back to the question asked.
Yeah.
The segment is mainly disk resident.
Yes.
And the bitmap, it turns out you have to, retrieve a lot of rows.
Yes.
A major subset of rows.
Yes.
So you end up scanning the whole segment.
Yeah. Yes.
What's your support for aggregation across segment boundaries? Is there any?
Like there is no, if I understand the question correctly, there's no like limitations of scanning like any segment boundaries. It's really like segments are these self-contained objects, and like what each node can do in parallel is just scan their portion of the segment, and then at the broker level, there's some merging of results that occurs. So at the higher level, at the broker level, there is like a result merge step.
Also, what's your consistency model?
So most of the data that we have in the cluster is immutable. Our segments, for the most part, the vast majority are immutable. So in that sense, like replicants are just exact duplicates of the data. So we don't really have any issues with reconsistency there. Druid has somewhat limited supports for write. Write would be really like ingesting an event stream and then building an immutable representation of that event stream. So Druid is like designed to work with like event data and data that has some notion of time. If you wanted to do like an update to some older set of data, the only option there is to rebuild that immutable block which holds like that event that you want to update.
Wait, sorry, going back to
Yeah.
my original question.
Yeah.
Let's say if the user wants to tell, I understand most of our queries are aggregation based on, say, products or
Right.
locality columns, but
Right.
what if the user wants to understand what's my sales bucketed by, let's say, revenue? Are you going to fall back to some brute scan, or you're just not going to answer that query at all?
Can you elaborate like sales bucketed by revenue? Like how many
Let's say
sales that
I
have
want to
within
find out
this
how many
revenue
sales I
range?
have greater than $100,000.
Okay.
That's gonna.
Yeah, so if the user kind of wants to understand, like if how many sales do I have that are greater than 100,000, then we really have to like scan through the data and understand like how many values are actually greater than 100,000.
Is that built into the system, or is it?
The ability, like we have support so that you can do like sort of more arbitrary filters across like any column, but some of that functionality is a lot slower than sort of.
It's going backwards
Yeah.
and forth.
Yeah.
Is there any way to construct historical segments that are derived from other historical segments? Like in Reynolds' example, you could say, then maybe make a new dimension that is sale is greater than 100,000 or not. Build that once and then query on it quickly.
I mean, yeah, like that's completely possible. Our customers actually have not had a use case like that. Like you can rebuild a historical immutable segment with like a different set of columns or a different set of dimensions with whatever information that that you actually want. So I think like Vertica does something similar to this, where they build their blocks of data based on like queries that they think are going to be issued like more often than others, or like specific use cases. But we do support. We can theoretically support it. It's just we haven't actually done it yet.
Is there, what was the, I looked at Druid a while ago, so maybe this isn't a current question.
Okay.
Are you doing any support for SQL queries at all?
That's a great question. So, right, I don't know if you're familiar with the query API at all, but it's like purely JSON based. You're sending JSON blobs, which are great if you're programmatically generating them, but if you're like writing by hand, they're a pain.
Yeah.
We built an R package to work with Druid for like analytical purposes. We started building out a limited set of SQL functionality on top of Druid. I think we're actually going to open source that sometime in the near future. There's a few things that Druid can't do. Like Druid right now has no native support for joins. So there are certain like SQL queries that would not work in Druid right now.
Okay.
Any other questions? Thank you.